Okay, so today we're continuing to talk about entropy and how it affects our cycles. And today we're going to use it as another useful tool to analyze and compare real cycles to those that are isentropic. So we're going to develop another methodology for looking at best case scenario. You know, with heat pumps and heat engines and refrigerators, we had the reversible case was the best. So we compared it to like the Carnot cycle or the reverse Carnot cycle using the temperature of the high and the low temperature reservoir to calculate an efficiency, which was the best possible max efficiency. Well, we're going to do something similar today with steady flow engineering devices to develop isentropic efficiencies, meaning that if this particular engineering device is acting as something that is adiabatic and reversible, then we can calculate its efficiency and compare it to, or calculate its work and compare it to the actual work input or output of a real device, and develop a term for efficiency that way. So keep in mind that as we're working through these equations, again, specific assumptions may apply, that you have to know and remember what assumptions can be made and which assumptions should be made for particular scenarios, and then which equations are applicable. So take note of that. It's important to remember. We have a new homework assignment that is due next Thursday, so 1 week from today. These problems are not too bad, but they will require a little bit of time. They're not difficult to solve, but they require multiple steps, and so we'll cover a lot of the topics today that will be on the homework, and a little bit next Tuesday. Reversible steady flow work is work that is done along a path that is considered to be reversible, meaning that if we were to do the opposite of what we did to get from point A to point B, we would be able to get back to point A following the exact same path without any net effect on our system. So for a closed system, we define reversible or quasi-equilibrium boundary work as the integral of P dV. And it's beneficial for us to develop a similar concept for open system steady flow devices. And we've looked at this already in a sense because we've identified something called flow work. Okay, well now we're going to develop an equation for flow work that allows us to apply a similar approach that we did, similar to what we did when we were dealing with closed systems. But now we're going to be looking at open systems, so it's another equation that we can use. So using what we know about the systems and their relationship to entropy, we now can develop this equation for flow work. So we needed some additional background and information before we could develop it, because it relies on the Gibbs equation, which relates entropy, enthalpy, specific volume, and pressure, and internal energy one to another. So if we look at the steady flow engineering device energy balance, if it's undergoing a reversible, internally reversible process, we have it in terms of partial derivatives on Q and work. So net Q in minus net work out is equal to dH plus dKE plus dPE. Okay, now we remember that this del Q reversible, we defined it as equal to TDS, which was also found to be equal to dH minus VDP via the Gibbs equation, Gibbs second equation. So we can rearrange these terms, solve for the work, and put those two equations together, and now we have this, this equation for reversible work for a steady flow system that's equal to the negative integral of VDP minus the change in kinetic and change in kinetic and potential energies. And in the case where those are negligible, then we're just left with this. So the reversible work for a steady flow engineering device is the negative integral of specific volume times the change in pressure. Okay, note it's different than for boundary work. For boundary work, we had what? The integral of P dV. Okay, this is the dP. So we have pressure changing, but in general, with a steady flow engineering device, the specific volume is not always changing. Okay. So it is sometimes, we do need to know that functional relationship between volume and pressure if we want to calculate that integral in some cases. However, if we assume incompressible flow, which is a fair assumption with most liquids, then we can break the, or pull the specific volume outside the equation, and the reversible work is just equal to negative V, specific volume, times the change in pressure. And in the case where there is no work, meaning it's a nozzle or a tube or some other type of channel, we can set this equation equal to 0, so work reversible is equal to 0, and then we have this relationship here. And does that look similar or familiar in any way to another equation you may have seen? What? Okay, this is an energy balance, right? Energy equation. But more specifically, this is the form of the energy equation that's often used in fluid mechanics called the Bernoulli equation. And it's derived in much the same way, starting with energy balance. Okay, so Bernoulli equation also follows the first law of thermodynamics, which is that the energy components of the system have to equal out. So in pipes or flow networks where there is no work added or consumed by the system, it's just a flowing fluid, the relationship between pressure and velocity and any elevation change is given by the Bernoulli equation. Okay, all disciplines are interrelated. Okay, this energy balance is not just applicable in thermodynamics, it's applicable anytime there's a flowing fluid. Okay, also developed by Bernoulli. And it's interesting to see how scientists in different fields and different disciplines develop similar equations, and it ends up that they're actually equivalent and the same, which is good because it gives further evidence that it's these laws hold true. So if we're talking about flowing fluids in a liquid phase versus a gas phase, we have to remember that the work is going to be proportional to the specific volume. So if we have a work-producing device, in general, we would want to be working with a working fluid that's in a gaseous phase, because if it's going to be proportional to the specific volume of the fluid, something with a very high specific volume would be more beneficial to us, meaning it has a low density, in producing work. However, if it's a work-consuming device and we're trying to reduce the amount of work that it consumes, we would want something with a low specific volume or a higher density, like a pump. Pumps water, and a turbine deals with steam. Okay, so turbine is work-producing, a pump is work-consuming. Depending on what application or process you are applying this in, one may be better than the other. So in steam power plants, the pump compresses liquids and the turbine handles steam. Now, we had an example that we looked at where instead of having a condenser in a power plant, we just remove the condenser and we try to pump steam back up to the boiler. Well, here's further evidence that that's not a good idea. Not only are you risking damage to your equipment, but it takes a lot more energy to pump steam than it does to pump a liquid. Okay, because you have to use a compressor rather than a pump. It consumes a lot more energy. And so any potential savings that you may have by removing that condenser and not getting rid of the heat, you're going to more than make up for it in how much energy that is required to pump that steam back up to the boiler. That is just not really effective way to do it. Okay, so let's do some examples. And we're going to look at the two different scenarios. So one, we're using a pump to compress a fluid from 100 kilopascals to 1 megapascal. And we're starting as a saturated liquid. So in the liquid vapor region, if we're on the far left-hand side of the dome, it's a saturated liquid, and then we're going to compress that liquid to a higher pressure. Okay, so we'll end up still in a liquid state, but in the compressed liquid region rather than in the saturated liquid vapor region. The part B, instead, requires us to use a saturated vapor, so it's the same pressure, same temperature, but it's in a different phase, and increase the pressure again to 1 megapascals, but using a compressor rather than a pump. So we're going to compare the two and see which one requires more work input in order to accomplish the same pressure change. So this is a case where you would see that condensing your liquid prior to pumping it or compressing it will have a significant effect. Okay. So if we start just looking at property values, our state is 100 kilopascals, and it's a compressed, or it's a saturated liquid vapor mixture. So we're going to have to look up the V sub F, V sub G, H sub F, H sub G, S sub F, and S G at those two states. So at 100 kilopascals, what is V1 equals V sub F? Okay, 0.001043 meters cubed per kilogram. Okay, what's V2 equals V sub G? We'll say V1A and V2, V1B. Yeah. V sub G at 100 kilopascals. 1.6941 meters cubed per kilogram. Okay, so that's the initial state for the part A and for part B. So now we're going to look at 1 megapascal. And in this case, with state 2 in part A, we're going to assume that we're compressing this liquid, but it's a fairly incompressible material. So we're going to assume that V2A is actually equal to V sub F, which is also 0.001043 meters cubed per kilogram. Because even though we're increasing the pressure of it, probably not increasing the temperature by very much, and we'll just assume that it has the same specific volume at that point. Okay, so at 1 megapascal, V2B is going to be equal to what? We don't know yet. Okay. Yeah, it will be approximately equal. The temperature is not increasing significantly, although the pressure is increasing. If we look on, instead of a TS diagram, yeah, we're making the incompressible assumption. We don't know anything about temperature. All we know is that the pressure increases. And so because it's starting out as a saturated liquid and then it's becoming a compressed liquid, we're just going to assume that the specific volume doesn't change very much. Because one, we don't have any other information to find a different value, but also that. Okay. So let's look at this. The reversible work in is equal to negative integral from 1 to 2 of V dP. So if we make that incompressible assumption in part A, then we can just say that it's equal to negative V1, which is also the same as V2, times P2 minus P1, which is equal to 0.001043 meters cubed per kilogram multiplied by 1,000 kilopascals minus 100 kilopascals. So that's 0.9387 kilojoules per kilogram. Let me just look at something real quick. Work out is equal to negative integral VdP. So work in, we get rid of that negative. Okay, so 0.09387 kilojoules per kilogram. Now we look at the saturated vapor case. So in part B, we have the same equation, integral from 1 to 2 of V dP. But in this case, we don't know anything else about the second state. We don't know the temperature, so it's difficult to find a specific volume at the final state. We don't know the functional relationship right now between VdP, so we have to determine some other way to do it. So if we remember from Gibbs' second equation, it's TdS is equal to dH minus V dP. And in this case, if it's an isentropic compressor, then we can say TDS is equal to 0, and VdP is equal to dH. So we can put that into the equation. It's the integral from 1 to 2 of dH, which is just H2 minus H1, which is the work for a compressor. So we need to look up H at 1 megapascal, where S2 is equal to S1. So we need to go back to 100 kilopascals, and we need to look up S1 is equal to S sub G. So what is that value? S1 is equal to S sub G, yeah, because it's a saturated, this is S1B, so part B. Yeah, S1B is equal to SG. What is that value? Okay, 7.3589 kilojoules per kilogram Kelvin. And then we're also going to need H1B is H sub G, which is 2675.0 kilojoules per kilogram, kilojoules per kilogram. Okay, so when H is 1 megapascal and our entropy in part B is equal to the entropy at the initial state in part B, we can find by interpolation that H2B is equal to 3194.475 kilojoules per kilogram. So this H2 minus H1 is just 3194.475 minus 2675.0 kilojoules per kilogram, which is equal to 519.5 kilojoules per kilogram. Okay, so we're taking a fluid that's at the same temperature and same pressure initially. In one case, it's a liquid, and we're compressing it to 1 megapascal. In the other case, it's a vapor that we're compressing to 1 megapascal. And we can see how much additional work needs to be done compared to the liquid state. Significant. Okay, any questions on that example? All right. So we want to minimize the compressor work, and there are several ways to do that. One is we try to minimize irreversibilities, so friction, turbulence, a non-quasi-equilibrium compression, meaning we do it in like an oscillating or a pulsating matter that causes the fluid to oscillate or have turbulence. The second is to keep the specific volume small. So we want to try to compress things that have a lower specific volume, which means we often want to remove heat from this fluid. Fluid meaning it can be a gas or a saturated vapor, superheated vapor. We want to try to remove heat from it before we compress it, or sometimes as we compress it, or sometimes in between stages of compression. We can do that as well. We'll talk about all those different examples today. So another thing to keep in mind is be selective about what type of working fluid you use. You know, that's why in many cases we use refrigerant rather than water in compression processes, because they're more easily compressed at certain temperatures. So depending on our application, what we want to do, we would choose one over another, and that is to minimize the amount of work that goes into compressing it as we go through this cycle, because the compression process is necessary to increase the pressure back up to the same pressure as the heat addition cycle in a work-producing cycle. So there's three different methodologies that we can look at. The first is an isentropic compression. So this follows the, for an ideal gas, PV to the K is equal to some constant. So PV to the K equals constant means that we don't have any cooling. It's just an isentropic process, meaning we've minimized irreversibilities. So we've done this first half of the process to minimize the compressor work. But now we want to decrease, or now we want to look at ways to decrease the specific volume. So in the first case, we're not cooling it at all. We're not changing anything about the specific volume. And the work of a compressor will be equal to this equation up here, where K is the ratio of the specific heats for our working fluid. A polytropic process is PV to the N, where N is some value that's in between 1 and K. And this means that we're actually removing some heat from our fluid as we compress it. So depending on how close N is to 1 or how close it is to K, it will be more cooling or less. So the closer we get to 1, the more cooling that we perform upon our system. And then an isothermal process is one where the temperature is constant throughout the process. It means we have the maximum amount of cooling. We're removing all of the heat as we compress this fluid. So normally, a fluid temperature will increase as we compress it. However, if we're removing the heat and we keep it isothermal, this is the maximum cooling that is possible for the system to give us the least amount of work input. So note again that these equations are all valid for ideal gases, constant specific heat. The first one is an isentropic process. The second one is where we have some cooling involved. And then the third is an isothermal process. So you cannot apply any random equation to any process. You have to know what your process is, what your working fluid is, and whether or not specific heat can be approximated as constant. So let's just look. On a PV diagram, we're looking at the area under the curve or to the left of the curve as the work consumption. So we can see certainly that the isentropic process is going to have a greater work input than polytropic or isothermal. And because work is equal to VdP, instead of looking at the curves this way, we look at them kind of sideways. So the area to the left of the curve under it that way is the total amount of work. And then the isothermal process, will, of course, will have the least amount of work under that curve or to the left of that curve. Cooling a gas while it's being compressed is not always practical or feasible. And so sometimes we will undergo what's called intercooling in a multi-stage compression process. So we'll compress it to some intermediate pressure, cool the gas back down, and then compress it again, or cool the fluid back down, I should say. It's not always a gas necessarily. In this case, it would be if it's an ideal gas. But we want to perform this intercooling process when it's too difficult to try to remove heat from a compressor. Because generally, we like to insulate the compressor and not necessarily, you know, add fins to it or you know, have it immersed in a cooling bath to try to remove heat as things are being compressed. It's not usually viable to do that in a consistent way that doesn't degrade the quality of the compressor over time. So compressing in between two stages is a little bit more practical, although it involves now creating two compressors. The work will be minimized. Even though you have two compressors, it will be a less work input overall than if you had one compressor together, because you can perform the intercooling. So in these two processes, the work will be minimized best or most effectively if this Px, or this intermediate pressure to which we are compressing, is equal to the square root of P1 times P2. Or in other words, if that ratio Px over P1 equals P2 over Px holds true, that we want to minimize, if we want to minimize the work, that's the intermediate pressure which we should shoot for, and that's what minimizes these equations if we were to solve for that. So multi-stage compression looks like this. We have some initial pressure at state 1, and as we compress up to this intermediate pressure, P sub x, you can see the temperature of the system will increase. But then we apply this intercooling process that cools back down to our original temperature, and then we compress again up to P2. So it serves to minimize the amount of work done. If we were to just compress all the way up to this point here without this intercooling process, then we have all of this additional work under the curve or to the left of the curve that we would have to account for. So we save a certain amount by doing that, that it's effective to do it that way. Because cooling often is a passive process that doesn't require a work input. So let's do another example of that. We're going to look at several different cases of compressing air. We're going to see how much work is consumed per unit mass if it's isentropic compression, polytropic compression with n equals 1.3, isothermal compression where n will be equal to 1 and we use an alternate equation, and then if we have two-stage compression with intercooling with a polytropic exponent of 1.3. Okay, so we have 4 different cases, and this is very similar to a homework that you have. So it's important to understand the distinction between the 4. And we should see that there's a reduction of work input from A to B to C, and then D will be somewhere in between. It will be better than the polytropic case, but not necessarily better than the isothermal case. Because the isothermal case, we remove all of the heat as we're compressing, whereas in the two-stage process, we remove it in between the 2 stages, but we're not able to maintain the temperature constant. Okay, so in part A, the compressor work in for isentropic process is KR T1 over K minus 1, P2 over P1 to the K minus 1 over K minus 1. So in this case, K is equal to 1.4. Our R value is equal to 0.2870 kilopascals times meters cubed per kilogram Kelvin, which is the same as kilojoules per kilogram Kelvin. T1 is equal to 300 Kelvin. P1 is equal to 100 kilopascals, and P2 is 900 kilopascals. So if we put in all the numbers for that, we get 1.4, 0.2870 kilopascals in unit times 300 Kelvin divided by 1.4 minus 1. Quantity, P2 over P1, 900 over 100 to the K minus 1, 0.4 over, K minus 1 over K over 1.4 minus 1. And we find that our work in is equal to 263.21 kilojoules per kilogram. Okay, so that's part A. This pen is no good. Part B, we now use the polytropic equation. So the work of a compressor in is equal to NR T1 over N minus 1, P2 over P1 to the N minus 1 over N minus 1. And in this case, N is equal to 1.3. So if we put in all the numbers for that, it's the same as this equation here, except for we have 1.3 instead of 1.4. We get the work of the compressor in is 246.39 kilojoules per kilogram. In part C, the isothermal process, compressor work is simplified even further. So in an isothermal process, it means that this n goes to 1. So we have RT over n minus 1 is a 0. This equation blows up. We can't use this direct form of the equation. We have to go back to the original integral from which it was defined and start there. And if we do that, then we get RT natural log of P2 over P1. So in the isothermal case, the T is 300K. It's not changing throughout the process. So RT, natural log of P2 over P1, we get 189.18 kilojoules per kilogram. Okay, so those are A, B, and C, and you can see that they are in order from most to least work consumed. So now we're going to look at the multi-stage compression, which we would expect to be in between the isothermal case and the polytropic case. Because isothermal is still the best case scenario, but it's not always practical to remove all of the heat to keep the temperature constant the entire time. Okay, so for this part D, we first have to determine the intermediate pressure to which we want to compress. So it's P1 times P2 to the 1/2 power, or in other words, the square root of P1 times P2. So it's the square root of 900 kilopascals times 100 kilopascals, which is 300 kilopascals. So we're going to compress from 100 kilopascals to 300 kilopascals, remove some of the heat, and then compress from 300 to 900. So then our equation, where n is equal to 1.3, it's similar to the equation for the polytropic process, nRT1 over n minus 1, P sub x over P1 to the n minus 1 over n minus 1 plus nRT1 over n minus 1 P2 over P sub x to the n minus 1 over n minus 1. Where P1 is 300, or no, P1 is 100, P sub x is 300, P2 is 900, n is 1.3, and then the temperature value and the R value is the same in both cases. So putting in all the numbers for that, we get each side is equal to 107.66 kilojoules per kilogram. And we find that that total work in is 215.32 kilojoules per kilogram. So understanding what's happening in this process of compression and trying to minimize the compressor work, basically what we're trying to do is decrease the specific volume. And we do that by decreasing the temperature of the working fluid. We can do that in an isothermal manner by removing all of the heat. We can remove some of the heat. We can compress it to an intermediate stage, remove the heat, return it to its original temperature, and then compress again to a higher pressure. That all four of those processes work. And they all have different ramifications in the requirements for your design system. So you may not be able to remove heat as you compress it, or you might be able to. Depends on the cost of that. Okay, so we have irreversibilities in our systems. We can analyze the reversible case and look at our actual case and sort of compare them to one another and determine something called the isentropic efficiency. So these ideal processes that we're estimating as isentropic give us our theoretical limits, and then as we compare them to the actual processes, we can determine this efficiency. So let's look at a bunch of steady flow engineering devices. First, we'll look at turbines. And so it's the ratio, the isentropic efficiency is the ratio of the actual work output to the work that would be achieved if the process was isentropic. Okay, so it's actual turbine work divided by the isentropic turbine work. And if we neglect kinetic and potential energies and assume that our turbine is adiabatic, then when we perform the energy balance for each case, the actual case and the isentropic case, we find that the work per unit mass basis is just equal to the change in enthalpies for the turbine. So in the actual case, we're going to have some exit pressure that's the same, but instead of being an isentropic process, we're an actual process, our enthalpy change is actually going to be slightly lower than it would be for the isentropic process. So when we compare those two and we calculate the efficiency, the work input required, or the work output created by the actual turbine will be less than that created by an isentropic turbine. And so finding the ratio between the two gives us this isentropic efficiency, which is another way of measuring how close we are to the isentropic case. Okay. So let's do an example of that so we can see how it works in practice. That if we have steam at 3 megapascals and 400 Celsius expanded to 30 kilopascals in an adiabatic turbine with an isentropic efficiency of 92%, determine the power produced by the turbine in kilowatts when the mass flow rate is 2 kilograms per second. So the mass flow rate does not change from the actual case to the isentropic case. The pressure difference does not change between the two. What changes is the fact that in the isentropic case, our entropy value is the same, but in the actual case, our entropy value will be increasing. Okay, so what we need to do is calculate the work required in the isentropic case and then use the isentropic efficiency to determine what the actual work required would be. Because in this case, we can fix the state for the isentropic system, but we can't fix the state if it is the actual system. We don't know enough about the second state in the actual system. Okay, so let's start looking at these states. So we have state 1, which is the same for both systems. We have state 2 actual and state 2 isentropic. At state 1, we know it's 3 megapascals and 400 Celsius, so we have a pressure and a temperature. It's a superheated vapor, so the state is completely fixed. The entropy and enthalpy can be looked up. So the enthalpy is 31.7 kilojoules per kilogram, and the entropy is 6.9235 kilojoules per kilogram Kelvin. That comes from table A6, superheated. State 2 actual, we know that the pressure is 3 megapascals. At this point, we can't figure out anything really else about it. But the isentropic state 2, we know that the pressure is 3 megapascals, and the entropy at state 2, isentropic, is equal to the entropy at state 1. So it's 6.9235. No, sorry. The pressure is not 3 megapascals, it's 30 kilopascals. Got to catch me on that. Okay. We know that S2 is equal to 6.9235 kilojoules per kilogram Kelvin. So we can use this value to calculate our quality, because if we look at 30 kilopascals and this entropy value, we find that we're in between S sub F and S sub G at this pressure. So 6.92, we find X2 is equal to S2S minus S sub F over S SG minus SF, which is 6.9235 minus 0.9441 divided by SG minus SF, which is the same as S sub FG, 6.8234, gives us 0.8763. And these come from table A5. So then we can calculate our enthalpy at the second state, assuming it's isentropic. We find that it's equal to H sub F plus X times HFG, which is 289.27 plus 0.8763 times 2335.3 kilojoules per kilogram. So we get 2335.7 kilojoules per kilogram is the enthalpy at state 2 if we're assuming our system is isentropic. So now we can calculate the work of a turbine out is equal to H1 minus H2. So the work of an isentropic turbine is H1 minus H2S, which is 3231.7 kilojoules per kilogram minus 2335.7 kilojoules per kilogram. So the isentropic work sub S is equal to some value. What is it? 896? Okay. Yeah. So 896 kilojoules per kilogram. So if we want to find the actual work, it's going to be 0.92 times the isentropic work, because the isentropic efficiency of a turbine is equal to the work actual over the work isentropic. So 0.92 is 824.32 kilojoules per kilogram. And if we wanted to find the power output of the actual turbine, we multiply by the mass flow rate, which is 2 kilograms per second. So we get 1648.64 kilojoules per second, or kilowatts. Now, let's say in this problem they say, okay, determine the work output or the power output of the turbine in kilowatts, and find the enthalpy at the final state, the actual final state. So what we could do is we could say, okay, we know our work actual is equal to this value. Work actual is also equal to H1 minus H2 actual. So H2 actual is equal to the work actual minus H1, or negative H2 actual is equal to the work actual minus H1, or H2 actual is equal to H1 minus work actual, if we needed to find the actual enthalpy at the turbine exit. Okay, does that make sense? So when you're solving these problems, you have to be very careful about defining your states, because there's 3 states here, not just 2. The initial state is the same for both, but the final state will be different. One will depend on whether or not it's isentropic, meaning the entropy doesn't change, and then the other one will be the actual output of the turbine, which is an increase in entropy. The same thing can be done for compressors, but instead of working at the work output, we're looking at the work input. So the work sub S and work sub A are flipped to give us our isentropic efficiency for a compressor. And so in the isothermal case for a compressor, we talked about how the isentropic case is good, but if we want to find the isothermal case and we look at the isothermal case, then it gives us actually an even better comparison. Because with a compressor, by removing heat, we can do even better than the isentropic process. Whereas with a turbine, you can't really do much better than the isentropic process. It's difficult to add heat to the turbine while you're compressing it or expanding it. Similarly, we can look at with pumps. And for the isentropic pump work, because it's also incompressible, we can replace this work sub S with V times P2 minus P1. So if we know just the pressure difference between the two, we can assume that it's also incompressible and that our pump work is equal to V times P2 minus P1, and then our actual pump work is equal to H2A minus H1. Okay, so these are all just steady flow engineering devices. We're undergoing the same analysis that we've done before. We're using the same principles to find properties. But in this case, we're looking at it as an isentropic process and then the actual process. So the actual process is what we've been doing all semester. The isentropic bit is a little bit new. So don't get confused and think that this is crazy new stuff. It's not. It's all the same stuff we've been doing. But now we're just looking at what we can calculate based on actual inlet and outlet conditions and comparing it to a more idealized case and then looking at some efficiency based on that. Does that make sense? Is it confusing or do you guys get it? You got it? All right. So let's do an example with a compressor. In this case, we have an adiabatic compressor, so we're not removing any heat from it. It's just an isentropic compressor, so it's not polytropic, it's not isothermal, it's not any of those other examples that we did. But it is still an ideal gas, which we can use some of those equations, but we don't use the work of the compressor based on some of those other ones. Okay, so we want to find the isentropic work, and then we'll use that to determine the actual work. So it's compressed from 100 kilopascals and 20 Celsius to a pressure of 700 kilopascals at a steady rate of 2 kilograms per second. We want to determine the power required to compress the air if the efficiency is 95%. So again, we'll look at the isentropic case, calculate how much work is required there, and then because the efficiency is given to us, we can determine how much work is actually required based on that efficiency that's given to us. Okay, so if we're assuming air is an ideal gas, we're going to assume constant average specific heat. We know that work dot in is equal to m dot times H2 minus H1, and this can be H2 actual or H2 isentropic. It's also equal to m dot C sub P times T2 minus T1. So in the tables for air, it's a little bit more difficult to try to assume in an isentropic process, find the entropy at state 2 and then look it up, because you have to actually go to some other equations to do it with the tables. So it's a little easier to use this assumption of constant average specific heats. But we have some additional relationships that help us relate temperature and pressure for the compression of an ideal gas in an isentropic way. So T2S over T1 is equal to P2 over P1 to the K minus 1 over K. So we use this to solve for T2S. So T2S is equal to T1, which in this case is 20 degrees Celsius. We have to convert that to Kelvin, so that'd be 293 Kelvin multiplied by P2 over P1, which is 700 kilopascals over 100 kilopascals. to the K minus 1 over K. And in this case, we're going to use 1.395 minus 1 over 1.395. Yeah, we look K up from the table. So K for an ideal gas operating around 300, 400 Kelvin is 1.395. So we can find T2S is equal to 508.3 Kelvin. So then we go back to our equation of the work dot S is equal to the mass flow rate, which is 2 kilograms per second, multiplied by C sub P, and in this case, C sub P is equal to 1.013 kilojoules per kilogram Kelvin. So m dot times C sub P, 1.013 kilojoules per kilogram Kelvin, multiplied by T2, 508.3, minus T1 is 293 Kelvin. So we find the isentropic power input for this turbine is 436.3 kilowatts. Oh, sorry, compressor, not a turbine. So the isentropic efficiency for a compressor is W dot S over W dot A. So W dot A is equal to this W dot S divided by the compressor efficiency. So it's 436.3 divided by 0.95. So we find that the actual work input or power input to this compressor is 459.3 kilowatts. So again, comparing the idealized case to the actual case to determine, if we have a given isentropic efficiency, we can calculate our actual work. If we somehow calculate an isentropic work and an actual work, we could calculate the efficiency. So depending on what information is given to you in the problem, this is the basic process. Now in this case, because we have air rather than water or refrigerant 134A or some other working fluid, we can use those relationships that deal with ideal gases. We cannot use those relationships for a problem with water or with refrigerant. We have to use the property tables. We can only use them for ideal gases. So be careful about that. We can also find isentropic efficiencies of other devices, other steady flow engineering devices that don't have any work interactions with them. So what we're trying to look at is kinetic energy change instead of the work input or the work output. So if we find the actual kinetic energy at the exit and compare it to the isentropic kinetic energy at the exit, that's just a ratio of the square of the velocities. So if we have a really small inlet velocity, the V1 essentially goes to 0. We can calculate that H1 is equal to H2A plus V2A squared over 2. That comes from the energy equation. So if we did the energy balance for an adiabatic nozzle with no work input, we'd have the delta H term, the delta kinetic energy term, and a delta potential energy term. In this case, potential energy term goes to 0. If our V1 is very small, it goes approximately to 0. So then we can rearrange and solve for H and in terms of V. And then the isentropic efficiency of a nozzle is H1 minus H2A over H1 minus H2S is another way of putting that. So we can look at the squares of the velocity, where we can look at the enthalpy change from the inlet to the exit. So let's do a quick example with that. With air entering an adiabatic nozzle, at 200 kilopascals and 950 Kelvin at a low velocity. So that tells us that the initial velocity is low. They're not telling us a value, so we're just going to assume it's low enough to be negligible, and is discharged at a pressure of 80 kilopascals. So we know the inlet conditions, the pressure and the temperature. We know the outlet pressure, but not the temperature. We do know the isentropic efficiency of the nozzle is 92%. So we want to determine the max possible exit velocity, which would be the isentropic case, and then the exit temperature and exit velocity of the actual air. So if we're looking at this, first we're going to look at the isentropic case. So we know the ratio of the pressures going in and out of the nozzle, and we have some equations that help relate pressures one to another to find exit conditions. So we know state 1 is at 950 Kelvin, and if we go to the ideal gas table, we can look up directly the enthalpy of state 1, because it's only dependent on temperature, is 989.235 kilojoules per kilogram. And then we're also going to look up this reduced pressure because we need it to find the exit state. So state 2S, assuming the isentropic case, we have a pressure of 80 kilopascals. State 1, the inlet pressure is 200 kilopascals, P1. So this comes from the table. And we're looking it up because for an isentropic process of an ideal gas, we have an additional equation that relates the pressure of the inlet to the outlet of any steady flow device. That's PR2 over PR1, this reduced pressure ratio when entropy is constant, is equal to P2 over P1. So we can solve for PR2 is equal to P2 over P1 multiplied by PR1. So P2 over P1 is 80 kilopascals over 200 kilopascals multiplied by this PR1 that we looked up in the table at state 1 is 93.14, which is a unitless quantity, which gives us 37.256. So then we go to the table and we say, okay, where on the ideal gas table for air does P sub R equal this value, 37.256? So we go, we look through the table, we find, it's in between two values. We interpolate to find H2 sub S is equal to 767.33 kilojoules per kilogram, which means that it's around about 760 Kelvin, 767, something like that. So it would be good practice for you to follow this step, make sure that you can get this same enthalpy value in the table. So then we can calculate, let's see, we want to determine the maximum possible exit velocity. So V2S squared over 2 is equal to H1 minus H2 sub S. V2S is equal to 2 times H1 minus H2S square root. So we have H1, we have H2. We can calculate this to be 666 meters per second using the values given. The exit temperature of the isentropic case, we need to determine the exit temperature of the isentropic case is easy to find based on the table, but we want the actual case. So if we compare the two together, the nozzle efficiency is equal to H1 minus H2A over H1 minus H2S. So H2A is equal to the nozzle efficiency multiplied by H1 minus H2S minus H1, and that's a negative. So we can solve for H2A. using the nozzle efficiency is 92%. This H1 value is 989.235. H2S is 767.33. Plug those all in, and we find that H2A is 785.08 kilojoules per kilogram, which corresponds to a T2 actual of 766.3 Kelvin. Okay, so we found the isentropic, or the max exit velocity, the actual exit temperature, and now we want to find the actual exit velocity, V2A, which is again equal to the square root of 2 times H1 minus H2 actual this time instead of isentropic. We plug in the numbers for that, we find it's 639 meters per second. And it's always a good idea on these problems that as you're going through and you calculate and you find, you know, like say an exit velocity for an actual case, it should be lower than the isentropic case. So always do a reality check and make sure that you're getting the right answers there. Yes? What is the reduced pressure? Why was that on the chart? Okay, so the reduced pressure it's a quantity that we talked about in the last lecture. And let me just pull that up real quick. Hold on.